Okay, so welcome back. Before we start today, does anybody have any questions for me? So if you remember last class, we were looking at skip lists. That's these things you get, or you imagine getting them by starting with a list and repeatedly taking each element of your list and tossing a coin to decide whether or not that thing will get promoted to another list further up, and then doing the same thing with that other list further up. So maybe you get some structure that looks like this. A whole sequence of lists, which we call L0 for the first one, L1 for the second one, L2, L3, and so on. And on the front of this whole structure, you tack on an extra sort of dummy node called the sentinel. And the sentinel doesn't store any data. It's just there so that it can get the front of each of these lists. So you end up with some structure that looks like this. And we analyzed this, we started to analyze this. Well, before we analyzed it, we showed that it can do two things. One is you can use it to create implement a sorted set where all the operations take order log n expected time. And the other is to show that it can implement a list where all the operations take order log n expected time. So that includes adding and removing anywhere in the list. So unlike other lists we've seen, add or remove anywhere you want, it's still quite fast. Not quite constant time, but still pretty fast. And all of that relied on something which we hadn't proven, which is when you look at a particular element of the bottom list, I don't know, let's call it X, and you look at the search path for X, so that's the greedy path that always tries to go right, unless going right would take it to X and or beyond, in which case it goes down. We call that the search path is the greedy path that tries to make the most progress to the right. Well, when you look at that thing, the claim was that for any X, the expected length of the search path X is at most 2 log base 2 of n plus a constant. Okay. And we saw what log base 2 of n means. That's this thing that if n is 4 billion, then log base 2 of n is 32. So you can search for, in one of these lists that contain 4 billion elements, and to get to any one of those elements, you expect to have to traverse about 64 edges. So 64 out of 4 billion is pretty good. And we haven't quite proven this yet. Instead, we had started with some simpler stuff. And the first thing, basically, that we had done was we convinced ourselves that for a particular let's say value of X, the probability that X makes it into probability that a particular element X in the bottom list is in list L0, well, that probability is 1. So let's check that. 1 over 2 to the 0 is 1 over 1. So indeed, probability 1, X is in L0. What about L1? Well, it has to, in order to make it from L0 into L1, you have to toss a coin that comes up heads. That happens with probability at half, which is 1 over 2 to the 1. And in order to make it into L2, you have to toss a coin twice. It has to come up heads both times. And that happens with probability a quarter. So that's 1 over 2 squared. And that's true for all I. And from that, we deduced that the expected size of Li, and that's not counting sentinel, is n over 2 to the I. You start with n elements in the bottom list. Each one has probability 1 over 2 to the I of making it into the ith list. And so the expected number that you get is n over 2 to the I. Okay. And if you really wanted to, we'll see how you can do that, maybe a little more formally or something similar. Sure. Okay, so that's the expected size of Li, and that means total expected size of all lists, not including the sentinel, is n plus n over 2 plus n over 4 plus n over 8 16 plus dot. This is a little bit imprecise, so really what we're saying is this infinite sum as I equals 0 to infinity of n over 2 to the I, and the value of that sum is exactly 2n. Okay? So, any questions about this so far? So this structure isn't too big. You might be worried because we start with one list of length n, and we keep building more and more lists on top. You might be worried that that's using a lot of space. It's not. It's only using about twice as much space as a single list of length n. And in fact, if you count the space carefully, you'll see it's using, on average, 2 pointers for each item that's in your skip list, which is about the same thing as a doubly linked list does. So it's really not a ton of space. Okay. All right. So we want to analyze the length of this search path. So the search path has a couple of components. Sometimes the search path goes right, and sometimes it goes down. So maybe we can start by analyzing how many times the search path takes a step down. And well, the search path only goes right or down, and it basically takes one step down at each level, including the last one. So really what we're asking is, how many levels are there in this structure? Okay. And so that's called the height of the skip list. In this case, the height is 2. There is no level 3 in this one. Okay? And of course, it's always possible if you pick any any value for the height, let's say 1,000, it's always possible that the skip list has height 1,000, because even if there's only one element in it, there's some chance that I tossed coins for that one element and it came up heads 1,000 times in a row, so the height of the skip list is 1,000. So we we're asking again a question about the average height or the expected height in this case. So we want to know, on average, what's the height of one of these things if it stores n elements. Okay. So let's see how we would do that. And before that, let me just write down carefully a statement that somehow writing this a little bit formally, we would write the expected, that's what the E is for, size of Li is equal to n over 2vi. Okay. So we like to study the height of this thing. Well, it turns out that there's a nice trick that one can use when trying to do things like study heights or lengths of search paths or whatever. And that's a trick that's called defining an indicator variable. Okay. So it's basically, when you don't know how to proceed, understanding, knowing the height of one of these things looks complicated. So just keep making definitions, keep rewriting what it is you're trying to figure out, and then maybe with the right definitions, it will just somehow become obvious what you're trying to do. I mean, the answer will become obvious to you. So let's write this height in a different way. So what I'll do is I'll define this variable, I sub I. Now it's what's called an indicator variable, which means it only takes on two values. It's either 0 or it's 1. So I sub I is equal to 0 if the list Li is empty. And it's equal to 1 otherwise. And there's one of these indicator variables, I sub I, for every I in 0, 1, 2, 3, all the way up to infinity. Seems like a stupid thing to do, a strange thing to do. And but let's just keep plugging away. So now we're trying to understand what's the height of this skip list. Now, is there a way to write the height in terms of these I sub i's here? Plus I2 plus I3 plus I infinity. What does that tell me? This is the definition of I sub I. What is this number here? Yeah. Yeah. It tells me the number of lists which are not empty, which is what we're defining now as the height, or maybe that's the height minus that's the height plus 1, depending on whether the height of this is 2 or 3. So let's call this height 3. So the height is 1 more than the index of the last empty list. So these I sub i's, they're just another way of writing down the height. And the height is this complicated thing. It depends on how many elements are in here, and how many of them make it up to, whether or not each one makes it up to a list, or whether none of them make it up to a specific list. But these I sub i's, they're quite a bit simpler. They're just binary variables. They take on the value of 0 or 1. So the thing that we're trying to study is the height, which we'll define as, it's the sum I equals 0 to infinity of I sub I. And these I sub i's are 1, 1, 1, 0, 0, 0, 0, 0 forever. So when we take the sum, we just get 3 in that case. All right. height, we want the expected height, which means we want the expected value of this sum. Okay. And since many of you haven't learned any probability yet, you haven't seen this, but one of the nice things you can do with expected values is apply a property called linearity of expectation, which says that if we have two variables x and y, then the expected value of x plus y is just the expected value of x plus the expected value of y. So if I apply this repeatedly, what that tells me about a sum like this is that the expected value of the sum is the sum of the expected values. So I'm trying to figure out this expected height, and I've boiled it down to this problem here of figuring out these little individual expected values. Okay. So now we need to do something to get these expected values here. And in fact, all we're really trying to prove is some kind of upper bound. Remember, the statement here is always at most. And so we'll be happy if we can prove some upper bound on these expected values. So let's see what we can say about I sub I. So a couple of things we can say. I sub I. Tell me something trivial. I sub I is less than or equal to what? That's good, that's trivial. I sub I is less than or equal to 1. Agreed? It's either 0 or it's 1. Both of those are less than or equal to 1. So there's something completely trivial, but nevertheless useful. And so, since I sub I is less than or equal to 1, if this is true always, then it's certainly true if you look at the average value of I sub I, the expected value of I sub I. That's less than or equal to the expected value of 1. The expected value of 1 is 1. So if it's always smaller than 1, then on average it's smaller than 1 as well. Is that enough? Could we just use that in our formula and we'd get it? Well, let's try. Okay, so we said this is less than or equal to 1. So this is the sum I equals 0 is less than or equal to the sum I equals 0 to infinity of 1, which is equal to infinity. Not quite. Not quite good. A little too good. We need another upper bound on these I sub i's. Can you tell me anything else about I sub I? Less than or equal to something. Something that we already have an upper bound on. Yeah. Well, it's less than or equal to 2n, but in fact it's less than or equal to n. But that's weaker than 1, right? Except when n is 0. Case n is 0 is not so interesting. But that's close. I mean, you're basically comparing I sub I, which is an indicator, to some size. Yeah? No, well, I mean, that's still 2 to the I, 2 to the I minus 1. That's still no good when I gets big. This is a huge number. Yeah? Aha. So you say n over 2 to the I. It's not quite true, but I think what you're trying to say is you're trying to skip a step and say, well, the length of the list is less than n over 2 to the I, and what we know about I sub I is it's less than or equal reason that through for a second. If I sub I is 0, that means this list is empty. So this statement is then saying 0 is less than or equal to 0. That's true. On the other hand, if I sub I is 1, then we have a 1 on the left-hand side. And this list is not empty, so its size is bigger than or equal to 1. So both of those things are true. In either case, it's true. So it's really the case that I sub I is less than or equal to the length of L sub I. In fact, I sub I is just somehow a truncation where we replace the length of L sub I with the min of the length and 1. All right, so if this is true deterministically, then it's true when we take expected values. And that we can say something about. The expected length of L sub I, that's only n over 2 to the I. Okay? N over 2 to the I. Okay, so now we have two inequalities. Expected value of I is less than or equal to 1, and the expected value of I is less than or equal to n over 2 to the I. This one looks better because it's just 1. And this thing is n over 2 to the I. I mean, there's an n. N is this thing that goes up to millions and even billions, whereas this is just 1. But is this always better? I mean, is the first one always better? Or is it sometimes better to use the second one? So n over 2 to the I, let's I don't know, try and plot that. I'm going to go off screen. So here's the I axis, and n over 2 to the I, when I is 0, starts up here at n. And then at 1, n over 2 to the I is here at n over 2. And at 2, here it is at n over 4. And then at 3, here it is at n over 8. So it makes this exponentially decreasing curve. So this curve is n over 2 to the I. The thing we're comparing it to is 1. So somewhere down here on this axis is 1, like this. Never changes. So does n over 2 to the I ever drop below 1? Yes. In fact, it gets arbitrarily close to 0. And where does this crossover happen? When is n over 2 to the I equal to 1? Yep. When n is equal to 2 to the I, yeah. So that's just multiply both sides by 2 to the I. So that's the same thing as saying n is equal to 2 to the I. And when's that? How do we solve these things? Yeah, so we have an exponent here that in the exponent is the thing we're trying to solve for. So whenever you have that, you take the logarithm. So I take the logarithm of both sides. Log n is equal to log 2 to the I. And 1 base 2. Now, remember, informally, the definition of log base 2 of x is the number of times we can take x and divide it by 2 until we get down to 1. So, what's log base 2 of 2 to the I? That's just I. So, I is equal to log base 2 of x when n over 2 to the I equals 1. So these curves here, they cross right at this point. Log base 2 of n. Up until that point, 1 is smaller, but after that point, n over 2 to the I is smaller. And it gets smaller really quickly, right? At this point, they're both equal to 1, but then after that, n over 2 to the I becomes half, quarter, and 8 to 16, very quickly down to 0. All right. So we'd like to use that here. We have this sum, it's an infinite sum. It starts at 0 and goes all the way up to infinity. And we have two inequalities that we can use on the terms of this sum. One of them says they're all less than or equal to 1. The other one says they're all less than or equal to n over 2 to the I. And so we'd like to use whichever one is stronger. Let's write this sum out in a little bit longer way. So this sum is, we can write it, well, we can split it. So I'll write it longhand, and then we'll write it in this summation of this again. So this is expected value of I0 plus the expected value of I1 plus the expected value of I2, and so on, plus the expected value of I sub log base 2 of n plus the expected value of log I sub log base 2 of n plus 1 plus the expected value I sub log base 2 of n plus 2, and so on, off to infinity. So this is just me writing out the sum longhand. It has infinitely many terms, but focusing in on a particular, there's the beginning, and then there's a particular place where the interesting stuff happens. When we get to log base 2 of n, that's the part that we're interested in. Okay. So we split the sum into two parts. So for these first parts here, which inequality should I use bigger than 1? So maybe the last one is exactly equal, but in this range, in general, n over 2 to the I is bigger than 1. On the other hand, here, these guys, this is where I can use that they're all smaller than n over 2 to the I. In particular, this first one here, this number here is bigger than log n. That index is bigger than log n, which means that this thing is less than or equal to 1. And this one here is less than or equal to half of the previous one. So this is a half, less than or equal to a half. The next one in the series is less than or equal to a quarter, less than or equal to an eighth, less than or equal to 16, and so on. And now I can add all these things up. So how many of these are there? Well, there's log n plus 1. Right, this we count from 0 up to log n. So for these first guys, there's at most log n plus 1 of them. That's the first part of the sum. And what about the second part of the sum? 1 plus a half plus a quarter plus an eighth plus a 16, and so on. What does that add to? 2. This is the usual sum, the usual geometric sum. We did the same thing there, except we multiplied it by n. And so this whole second half is less than or equal to 2. Okay. So adding all this together, we get log n plus 1 plus 2 less than or equal to log base 2 of n plus 2. Okay? And so really the way to think of it is to say, look, up till the point level, up till you get to level log n, there's usually something in the list. After that, the probability that there's something in any of these lists above level log n decreases very, very quickly. Drops to a half, a quarter, an eighth, a 16th as soon as you get past the height of this thing is basically always close to log n. The chance of it getting much more than log n drops off very, very, very quickly. Questions there? So there's a couple of lessons here. One is we started with this thing, this height that we were studying, and really had no idea how to do it. So we tried to do something, tried to break it down, which we will continue to do. And the other thing that we did here is, well, we saw that once you break it down, you get this big, long, this infinite sum that has sort of two interesting parts where different things happen in each part. So for the first log n levels, yes, there's probably something in each of those lists. So we'll just assume there is. That's what when we replace this with 1, we're just basically assuming there's something in each of those lists. After that, we have a pretty good idea that there's nothing in those lists, that the lists get smaller very quickly, disappear very quickly. Okay. All right, so another little fact for us. I think I can erase this. So the expected height, where height is defined as the number of non-empty lists, is at most. So there's a few places where we use inequalities, so the best we can say here is at most log base 2 of n plus 3. We don't know that it's at least log base 2 of n plus 3. That would take a different kind of argument. But we're more worried. We generally worry more about our data structure taking too long and not working too quickly. Okay. So that means we can unqualify this thing. So we said the total expected size of all lists, not including the sentinel. Well, now we can remove this qualifier that says not including the sentinel. And once we add the sentinel back in, how many times does it occur? Well, it occurs exactly as many times as the height, so we get log base 2 of n plus 3. Okay, so now we really know the size of this thing. We counted everything, all the elements in the list, all the sentinels, everything. And we know that height, log n. We're still trying to get to this statement that says the length of the search path is at most log 2 log n plus a constant. And well, now maybe we have some hope. So the search path takes steps to the right and it takes steps down. So we can break it down into two parts. So if we're trying to study the expected length of the search path, length of the search path, well, that's equal to the number of steps down and plus the number of steps to the right. Right? And so we have an equality, so we can take the expected value of both sides. And we use linearity of expectation to say, since we're adding two things together, I'm just studying their expected values individually. Same way we brought this expectation inside the sum here. This is a simpler example where there's only two parts to the sum. All right, so this is the thing we're trying to study. We broke it down into these two parts. Do we know one of these already? Yes, which one do we know? Number of steps down. That's exactly the height. So this, we already figured it out. It's less than or equal to log base 2 minus 1. All right. So far so good, so we're halfway there. Now we just need to know the number of steps to the right. So it looks like we're going to try and say something like, I mean, if the proof ultimately finishes with the answer 2 log n plus the constant, it looks like we're trying to say something like, well, we expect to have log n lists, so we expect to take 1 step to the right within each list. That would give us the extra log n. We have to somehow formalize that, get that correct. So what we're interested in is knowing the expected number of steps to the right. Again, that's a complicated thing because it's the expected, it happens over a bunch of lists. So let's write this down, expand it out again, and say this thing, well, this is the sum of I equals 0 to infinity of the expected number of steps to the right in this I. Right? When in doubt, just matrix divide. You make it write whatever it is you're studying, this complicated thing, in terms of simpler pieces. So now we just have to study one individual list, basically, the list Li, generic list. Okay? All right. Yeah. This is exactly equal to. This part is exactly equal to. The number of steps to the right is equal to the number of steps to the right in L0 plus the number of steps to the right in L1 plus the number of steps to the right in L2. And so when you take expected values, they're equal also. Okay? So just so we have instead of writing this out longhand like this, I'll just define this thing as yi. Yi is equal to the number of steps to the right in Li. It'll make life easier for us. And now, I'm going to erase this, and then I'm going to write it out almost exactly the same thing again. Because the proof of this part is almost exactly the same. Yi we've defined as number of steps that the search path takes to the right in this house. So we want to make some inequalities on yi. So what's a trivial inequality for yi? Yeah. So I can't, if I'm in a list of blank Li, I can't take more than Li steps to the right. More than that, and I get past the end of the list. That would be following the null pointer. So yi is less than the size of the list Li. That's sort of that's the same sort of trivial one that we used before. And beyond that, we have to do a little bit more work. value of yi is less than or equal to 1. That would be great. But that's not immediately obvious, because it's certainly not true that the number of steps to the right in a particular list is always smaller than 1. Sometimes we may take many steps to the right. It's easy to draw an example like that. Yeah? It is always greater than or equal to 0, but inequalities like that with lower bound of the value of yi are going to help us. Because ultimately, yi appears in the sum, and we want to upper bound the whole sum. So the lower bound of yi won't help prove what we want to prove. So let's do a thought experiment. Imagine, this is a fun game to play on a Saturday morning. You have done something wild and crazy the night before, on Friday night. And on Saturday morning, you wake up and you find yourself here. You don't know how you got there, it doesn't matter how you got there. Now, where's here? Well, here is a node in a skip list. You're sort of lost, and so you would like to find your way back to some point that you know. And the point that you know is up here in the top node of the sentinel. Okay. So what you would like to do is, if possible, go up. And if that's not possible, you'll go left and then try again to go up. And if we think about this for a few minutes, the picture of the skip list is gone. If I start down at X in the bottom list, and I follow this rule of going up when I can and going left if I can't go up, then what I will trace out is the search path for X, but in reverse. So I get exactly the same search path, it just starts at X and goes to the top sentinel instead of starting at the top sentinel and going down to X. So let's say I've done this for a while, or I wake up and I'm at this node, and now I want to know, so if that search path is the same as the search path for X, well, I'm interested in how many steps the search path for X takes to the right in Li, which in the reverse search path is steps to the left in Li. So I'm interested in understanding if I wake up at this node, which usually happens because I've come up here from below, but it could be that this is L0, so I really did just show up here. But I'm interested in knowing how many steps I have to take to the left like this before I get to go up. All right. So, right, this is a picture of a node in some skip list. It's in the middle of the tower somewhere. It's at height I. It doesn't really matter. I don't know if there's anything up here yet, and I don't know what's over here exactly. Now, if I tell you nothing else, what's the probability that this thing gets to go up at this first step? 50%. So why is that? Well, if I tell you nothing else, then all I know is that this node appears in list Li, and it may or may not appear also in list Li plus 1. And, well, what determines that is a coin toss, whether a coin toss that we did at this point came up heads or tails. So half the time, you may be able to just go straight up. Never take a step to the left. So that would be 0 steps to the left in Li. The other half of the time, you do have to take a step to the left, and then you find yourself in the same situation again. And so half the time after that, you get to go up, half the time after that, you get to take a step to the left, and so on. So let's think about the big picture here. Really what we're doing is we're standing at this node, and imagine that we're tossing a coin. If the coin comes up heads, we go up and we leave. If the coin comes up tails, we go left and we repeat the experiment. So this experiment ends the first time the coin comes up tails. And the number of steps we take is the number of times the coin comes up heads before that. So I toss a coin, and it comes up heads, 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 tails, stop. And the number of heads that I get before stopping is the number of steps that I take. So first of all, if you toss a fair coin until it comes up tails, what's the expected number of times you'll have to toss it? Just a number. It's just one single number. If I toss the coin until it comes up tails, or until it comes up heads, rather, how many times do I expect to have to toss it?
2 times.
2 times. So the expected number of coin tosses until you see the first head is 2. Okay. Including the one that came up heads. Now, if that's true, if you believe that, which sounds fair, half the time it comes up heads, and you can write this down a little more carefully. Just using the fact there's a probability that it comes up heads is half. If you believe that the number of times I have to toss it is 2 before the first head, the expected number, then how many times do I have to toss it, or how many coin tosses do I make, not counting that last one? Not a fair question. Yeah. So 2 coin tosses till I see heads. How many coin tosses before I see heads? 1. 1 less. The last one was heads. So however many before that. Okay. So the expected number of so translating that back into what we're doing with skip lists, we wake up in the skip list, and we pretend, we imagine that these coin tosses have not been done yet, and then we try and figure out, well, how many steps do we have to take to the left before we reach a node that can go up, and the number of steps to the left, the expected number is 1. When you do it in terms of the original search path, that's the expected number of steps to the right. So indeed, we do get this inequality that we want, which is that the expected value of yi is less than or equal to 1. It's not true that yi is always less than or equal to 1, but on average it's less than or equal to 1. All right, and now, in case you missed it the first time, we can do the whole thing again. So we're over here. Length of search path is the number of steps down. We figured that out, plus the number of steps right. And then we started studying the number of steps right in each individual list. So now we're looking at the sum of the expected value of yi. Y equals 0 up to infinity. And we split that sum into 2 parts. One of them goes from 0 up to the floor of log n. The other one goes from 1 up to infinity. The same sum is just split into 2 at a natural place. And what should we say about all these yi's? We have two things we can bound them by. We can say they're all less than or equal to 1, or we can say they're all less than or equal to the expected length of Li. Which is more powerful? Less than or equal to 1, right? These lists, the first log n of them, they're actually in general pretty long. I mean, the bottom one is length n. So it's certainly better to say that the length is less than or equal to 1 than it is to say it's less than or equal to n. So all these guys here are less than or equal to 1. These guys, on the other hand, they're all less than or equal to the expected length of Li. And the expected length of Li, we already figured out, is actually equal to n over 2 to the I. So here's a whole bunch of 1s. Number of these things is log n plus 1. And here's another sequence that starts with something that's smaller than 1, same as before. So n over 2 to the I, when I is at least log n, is at most 1. And so this thing starts with a 1, something less than or equal to 1, and then continues with something less than or equal to a half, and then something less than or equal to a quarter, less than or equal to an eighth. So on. And that whole thing is less than or equal to 2. So in the end, we finish with the expected number of steps to the right in total across all lists is log n, is at most log n plus 3. That's what we needed to finish up over here. This whole thing is less than or equal to log n plus 3. Add to that the number of steps that we take down. And we get 2 log n plus 6, which indeed is 2 log n plus a constant. That's the constant. Yeah.
Why are you using log n? Oh, when is the plus 1?
Which plus 1? This plus 1?
Yeah.
Because we count from 0 up to log n. So if the floor of log n is exactly, so log n is an integer, then this is really counting from 0 all the way up to log n. And whenever we count from 0 up to x, there's x plus 1 terms there, right? This is certainly at most log n plus 1. All right. So that shows us that this expected length of a search path and a skip list is at most 2 log n. And that was the final piece of the puzzle to show us that skip lists have expected time order log n to do all of these operations, whether it's to implement the sort and set operations, or whether it's to implement the list inputs. So that was a good chance to ask me any questions. Yeah?
You said earlier in the class that nobody uses
No. I didn't say nobody uses skip lists in real life. Nobody uses top-down skip lists in real life. That's a different reason. Well, top-down skip lists are only my goal. Yeah?
Are we going to have to replicate this like on a test, this whole thing?
You might be asked questions about this, this analysis. So test, because there's the midterms and the final exams will be multiple choice, because there's 260 of you and only one of me. And so, you know, you may be asked questions about parts of this analysis on the midterm. So I don't expect you to be able to sit down and completely reproduce this, but you can certainly be asked questions about it. And you know, with some guidance, you should be able to reproduce little parts of this. Okay. Question now? All right. So then, what I think I would like to do in reality. So we've studied a bunch of list implementations, and you know, they're all mixed up in our head now, and they all have different running time guarantees, and it's not clear what all of this means. So let's just look at a few examples. So here I've written a little bit of code for testing list implementations. Here's the stuff that it does. So first, we add a bunch of elements by appending them to the end of the list. Okay, so every list that we've studied should be able to do this quickly. That's the main operation that list can support. So every list implementation. Then, and actually, the number of elements here will be 1 million. So n, the number of elements we add is 1 million. Next up, we add 200 elements at the front of the list. Some of the implementations we've seen can do this quickly, and some of them not quickly at all. So for instance, if I'm using an array stack, which is the thing that in Java is called an array list, is it fast to add elements at the front? Not really. That requires all this shifting of the, what are now 1 million elements in the list will have to be shifted out of the way each time we add a new element. Then I do some random gets. So I pick a random integer between 0 and the length of the list, and I get the index, or I get the value in that list. If I was using an array list, is that fast or slow? Fast. It's an array, right? You can get any element, constant time. So that'll be fast. What about if I was using a linked list? Slow. And what if I was using a linked list when I added the elements at the front? Fast or slow? Fast. Okay? So there'll be some kind of inversion there where the array list is slow for adding at the front, and then but fast for the gets, and the other way around for the linked list. Then I'll do a bunch of random insertions, picking a random location in the list and adding a new value there. With a array list, is that fast or slow? Slow. With a linked list, is that fast or slow? Slow, but for a different reason. They're both slow, but for different reasons. The array list is slow because you have to move a lot of stuff out of the way. The linked list is slow because it takes a long time to get to that location where you want to insert. Then some random deletions, which will have exactly the same kind of performance characteristics. And then removing a bunch of elements from the front, which, like adding elements at the front. And then finally, emptying the list by removing elements from the back. Okay. So let's try this. Okay, so adding 1 million elements at the end in an array list takes 0.2 of a second. Adding only 200 elements at the front takes longer than adding 1 million elements at the end. That's slow. That's a huge difference in the number of operations we did, and it still takes longer to do adding elements at the front. Getting a bunch of 200 random elements, super fast. We end up showing it to us in scientific notation, so there's something like 3 leading zeros there. Random insertions, slow because we only did 200 of them, and still that took about half the time it took to add those million elements in the first place. And notice that random is about, not exactly, but sort of twice as fast as adding at the front. And that's sort of what we expect too, because if you're adding things at random, you're on average adding in the middle, so you only have to move half the elements out of the way. Random deletions, similar. And removing 200 elements from the front, look at that, it's almost the same time it took to add those 200 elements at the front. Again, that's super slow, because it's, the time for that, for doing 200 of those is the same as the time for doing 1 million additions at the end. And then finally, emptying from the back, it's tiny, super fast. We can compare that to, so that was the implementation of java.util.array list. This is the implementation we discussed in class. Which actually does a little bit better. So adding 1 million elements is a little bit faster. Adding the 200 elements at the front, way slower. We'll see why that is in a second. So there's a lesson to be learned here about practical performance. The random gets, again, they're super fast because you're just looking in an array. So this is an implementation of the same idea, just one comes from the Java Collections framework, one comes from the textbook. Random insertions, again, they're way slower, they're 5 times slower. And random deletions, again, quite a bit slower, and removing from the front. So all these slow operations are about 5 times slower. And removing from the back is slower, but that's for a reason that, for a good reason. It turns out that this implementation of java.util.arraylist never shrinks the array. So it'll happily allocate 1 million elements when you insert everything, and then if you shrink it down to 50 elements, it'll sit there and hold on to that million, that megabyte, or probably 8 megabytes of memory that array is using. Okay, so, but still there was some stuff that's not explained. So we added these elements at the end, and we were actually faster than that implementation, than the collection framework implementation. But adding at the front, we were not so fast. And the reason for that is just an optimization that you can do, which is, if you remember our array lists, in fact, we can just take a quick look at them. When we add something to an array stack, we do, it's sort of the code that looks, the only thing you can do is you shift elements out of the way to make room for the thing that you're adding, and then you set the value, you increase the value. And it's not clear how you could make this 5 times faster. Anybody know how? Yep. No, because the resizing hardly ever happens. So it's not the resizing that's doing it. And the resizing wasn't really an issue because we saw that when we're just adding at the end, we're actually, this implementation is faster than the collection framework one. So here's something good to know. For loops like this, which copy big chunks of memory, there are much more efficient ways to do them. And usually those much more efficient ways involve, in the case of Java, they involve some native call. In the case of languages like C and C++, they involve calling some subroutine for copying big chunks of memory. So we actually have an alternative implementation of this thing called the fast array stack, which does the same thing, but instead of a for loop to shift those elements over, it uses a built-in Java method called system.arrayCopy. And system.arrayCopy is a native method which goes into a C subroutine which calls the fast routines for copying a chunk of memory. And it should be the case that that's about 5 times faster. So let's try it. And indeed. So now if we look at adding the 200 elements at the front, it's now comparable to what we were getting from the java.util. It's 5 times faster than this. And similar things happen with all the other random insertions, random deletions, and so on. So there's something to be